in the future. So yes, validation is very important, but how could you do the validation and build the trust in your model and your assumptions? And this is when it comes to do testing and instrumentation. Yes, this is not meant for any conventional structures, for small scale structures. This is mainly for bridges. We were looking into the entrance of one of the ports, so we had to do live load testing to determine what is the capacity of the structure. So load testing, why do we go to load testing? Yes, it considers the actual behavior of the structures. There are a lot of strength enhancing factors that we cannot account for in our design. We assume a simple beam action. In the structure analysis, we have to put the support, this knife edge support, which we always draw as a triangle. Nothing in life is a knife edge support. In reality, any member will be supported over a seating length. So all this idealization that we make for structure analysis, for design, yes, that's acceptable for design, from design perspective, but when you are assessing an actual structure, there is a lot of parameters that we cannot account for in the design, that it is wise to be looked at. And that's the beauty of the load testing, that those strength factors, we can design a structure as a non-composite. Believe it or not, there will be some unintended composite action between your concrete deck slab and your beams. Can you quantify this? No way, unless you test it. A lot of the secondary members, they contribute to your strength. Bracings, a lot of these members that we cannot account for in the design, they will provide some elastic support at your midspan. Testing can be static, can be dynamic. The static testing can be diagnostic or proof testing. The most common used is the diagnostic testing. So basically you are trying to put a load in the structure and look at the performance of the structure under that specified life. How can we load test structure? That's what we commonly use, at least in bridges. And we are privileged to be working with DOTD and a lot of those testing for bridges to evaluate structure or bridges mainly for loads that can go in those bridges. Most commonly we use those dump trucks. Don't underestimate those dump trucks when you see them on the highway. The axle load is 31 kg, and the two axles are 4.5 feet apart. So the total weight of this truck is 70 kg. Actually, when we design our bridges, according to the ASHTO code, our HN93, which is our notional design truck, is 72 kg. So this truck, when it runs on the bridge, it is actually what we're designing for. We sometimes can use counterweights, but it's not very common, but this was done for very specific projects, with the kind of larger scale projects. Just to show you pictures, it was of the same project. We had to load the two entire spans with trucks, and each one of those trucks weighed 390 kilos. So, and we actually, in addition, we had those counterweights in the middle between the trucks, and we had 6 trucks back to back. I will show this project. This was a project that we did last year in Louisiana. Just a picture of the trucks lined up on the bridge. This is a very special bridge, by the way. It's not a common highway bridge. Loading. When we load a bridge or a structure, can we just go ahead and put the load or the load that we are planning to put on the structure all at once? In the lab, we have the, I would say, the advantage of using hydraulic actuators. So you start applying the load gradually. 0, 1, 2, 3, until you reach your maximum test load. But in the field, how could you control that? And the easy way to do it, or the smart way to do it, is you start having the truck weight is determined. It comes you, the truck is loaded, so the load is determined. You start playing with your axle loads. So you start moving your load to increase your mid-span moment capacity if you are interested in the mid-span moment. So how you position your load, that is the trick. How you can start position the load to apply the load incrementally on your test element, so you don't overload. And definitely at every step or every position, when we are moving the load, we are comparing what we are measuring in the field, on the fly, to what we are predicting from our finite element analysis. And that's one of the beauty of the finite element, that we have to do it before the load testing as well, is to give you an idea how much strains you are expecting in your structure. So we just go load the structures, and while having the truck sitting on the bridge, oh, the beam is yielding, we'll be in trouble. So this also has to be combined sometimes with an assessment of the condition of the structure as well. And this is mainly the non-destructive testing. So you can do, like, for example, this is what we do: chloride ion penetration, inspection, infrared, ultrasonic. It gives you an understanding of the condition of the structure, and you have to account for that as part of your assessment as well. In instrumentation, that's the fun part. We instrument the bridges or the structures with gauges, so we can measure deformations, we can measure strains, and definitely we can measure rotations. This is an assortment of pictures from different projects. Just showing you pictures in instrumentation plans. This was 2 pictures from a project that we just presented today to DOTD. And then we'll show selected projects for some of the structures that we have retrofitted with FRP in the past, and I mainly try to focus on structures, old ones with approximately 30 years, so that this can reflect on the durability. Because this is always the question. Durability, yes, we have projects that have been sitting for 30 years that have been retrofitted with FRP, and they are still in service up to today without any problem. This bridge was in Florida, and I have to say that all of these bridges that were done in the past, they were done under Dr. Shehawi. I wasn't there for sure, because you will see some of them are like early 90s or late 80s, so maybe I was still in college. So this one was in Florida, done in 2005. It had the splashing zone issue, which is very typical for water structure. You have the splashing zone, so the high tide, water goes up and down, so you have the splashing zone. So you have corrosion, concrete. So to do that, they established this coffer dam. And now you can expose your column. You start cleaning, grinding, which is the surface preparation for the FRP application. So that's how the FRP and the epoxy start bonding to your concrete surface. So you have to have a surface preparation to establish the bond. Now I wasn't there, they did not have much time to wait for the concrete to dry, so we have to dry it quickly. So they start applying the FRP. This is the final product, shows you the 2 completed piles next to the ones that are not retrofitted yet. Another bridge from 1994 in Florida. You can see the corrosion on the longitudinal steel bars and the transverse. You can look closely, you will see that that's the extent of corrosion that you're looking at. Rupture of the stirrups. You know that when the steel bars, when they corrode, they swell. So they occupy a larger volume. And this is when you start seeing the spalling of the concrete and you lose your color. And that's mainly because of the corrosion. Removing all the damaged concrete, that's the only way. This is all bad concrete. You have to remove the concrete behind the steel bar so you can reach to the bar to clean it. Coat the bar, restore the concrete, apply the FRP. Coated bars after cleaning. The fun part, which is building the forms. We do that a lot on bridges that are impact damaged, so we build the forms up in the air with traffic running under the bridge. Pouring the concrete, that's your final product after the retrofit. This bridge was in New York. It's very close to the water. It has a flexure and a shear of the girders. Cleaning, removing of the concrete. You can see the rupture of the stirrups at the corner. Typically the corner is the stress concentration, so with the corrosion this is where the stirrup will give up on you. Then you start applying the FRP. For flexure, that's why it's a longitudinal. And you start looking into the transverse as well for shear. And that's your final product after the coating. We also apply some ultraviolet coating on the top of the FRP to protect it from the sun and to have the nice look. This was an interesting project. It was a new bridge. There was nothing wrong with the bridge, by the way, but they were building a new bridge between the 2 existing bridges. So this is an existing, and the contractor decided to have the my-jack in the middle, so they would have the spans, lift up the spans, put them in place, but the wheels were running on the exterior slab, that were deficient under this MyJack additional load, which is not definitely the design load. So we ended up strengthening the exterior slabs with the FRP, and they even requested that we do a load testing and we measure the strain in the FRP and the concrete as well. This is the fun project that I was talking about. This was back from last year. This is called the Dragline. It's a big excavator. It weighs 10 million pounds. And this load has to cross the bridge. And the owner of the bridge, they were concerned that the bridge could collapse or something could happen while the load is crossing the bridge. So we had to go and assess the structure, do load testing, determine if it is safe that this load can cross on the bridge. Just you can have an overview. This drag line is sitting on this SPMT, which is the self-propeller mounting transducers. They were having 46 axes. This is a 10 million pound. Just to give you an idea of this is the truck that we used for the testing. You can see the guy next to the truck. The truck weighs 390 kg. So we're talking about 400,000 pounds. This is showing this thing when it's crossing the bridge. It crossed the bridge in 85 minutes. We did the testing mainly, so we developed this chart so you can look at the relation between the stress and the moment on the beams, because when the load is crossing the beam, those were pre-stressed beams, and the bridge consists of 10 girders. They were almost sitting next to each other. There's no spacing. The girders were almost touching. And we have to ensure that when the load is crossing the bridge, we are not cracking the beams. So that's why, based on our analysis and the load testing and the modeling, we decided to reduce the load a little bit from 10 million pounds to 8.5 million pounds, so we are not taking the risk of cracking those girders. So this was for the superstructure. We had also to look into the substructure, the piles. And that's why we ended up loading the 2 spans from both sides and putting the counterweights on the top of the pile bends, and we measured the settlement of the pile, and you see the settlement after removing the load, it was almost nothing. There was no problem with the piles. By calculations and by records, those piles should not be strong enough, but definitely the piles, that's a big issue because the soil consolidates with time, so the piles get stronger. Conclusion. Fundamental understanding of structural analysis, no doubt. You need good engineering basis to be able to do anything. There is no doubt about that. Combined with practical engineering experience, plus what we call refined analysis techniques, correct? Which is the finite element in our case, not alone. Then you have to go into load testing and calibration. And I meant for this mainly for main structures, big structures, like bridges, if you have ports, docks. Knowledge of advanced material, so you have to know the material properties, you have to know how it behaves, where it can take tension, and what's your material properties. You have to develop an understanding of the material that you're using. The 5 parameters combined, yes, you can end up with an effective long-term solution for your structure. And I mean by long-term, we see this a lot of the time. We go to repair a bridge, and simply we are repairing the repair. So somebody have done a repair in the past, and you're going to repair the repair. And then you go and repair the repair. If you don't know what you're doing, it's not about patching material, it's not about just applying FRP. You have to have an understanding of the problem, find the appropriate solution. So this is a whole process. It's not just simply the material by itself. By this, I'd like to thank you for your attention. I hope I was intending to stay within the 25 minutes. I think I went a little bit longer. I hope not. And thank you so much for your attention. And if you have any questions, I'll be glad to answer any questions. Thank you.
You guys have any questions? You guys had lots of comments.
Just a question about the economic cost comparison with the FRP used compared with the gained strength of the structure?
That's always the cost is a very good question. If you're looking at the cost of the material itself as FRP, you cannot look at the cost of the material. We agree about that. You are looking about the cost of the solution. That's one thing. So you have to account for the cost of the material. You have to do, in other words, a life cycle cost analysis. As simple as that. So now when you do the FRP as a material, you have to account for all your direct cost and indirect cost. Most of the time, the FRP might be more economic if you do the life cycle cost analysis. Again, it depends on the nature of the problem. So I'm mainly talking here about structural repair. So I'm not talking about like cosmetic repair. There is like a spalling area of concrete, so you go and do the patching of the concrete. You have a crack, so you go and do epoxy injection. I'm talking about structural repair, which means you have a section loss, you are increasing your load carrying capacity. So the other option from FRP is to use steel plates or enlarge your concrete sections. You have to build an enlarged section or add steel plates. Sometimes it's not only the cost, sometimes it could be the accessibility, because you have a lot, sometimes bridges, they are crossing water, so you don't have the accessibility to go and build and pour. Sometimes it's the accessibility is the issue. So you have to do more of a life cycle cost analysis. If you do the life cycle cost analysis for structural repairs, most of the time you will end up maybe the FRP is an economic solution. Sometimes, maybe not. So we look also into other terms. It's not always FRP, but it's one of the very appealing options. Does that answer the question? Yes. Thank you.
I have another question. If there is a time, maybe I can teach.
So do you have any experience with using FRP in culverts?
In culverts?
Mm-hmm.
I did not strengthen a culvert or repair a culvert with FRP, but I don't see a culvert any different than any structure.
I mean, if the culvert has some problem with shear capacity, so how can we use FRPs in this?
Culvert has a shear capacity, so that's in the slab or in the wall?
Between the slab and wall, yeah.
That's a one-way shear?
I mean, I worked in culvert projects.
Because we know that slabs will never have a one-way shear problem, correct?
Yeah, but
it's a wide element.
But the old reinforcement detailing in Louisiana.
Yeah.
So it has like I mean the detailing of reinforcement was not like go into the.
But that's a flex. We are working on a big project on culvert for the DOTD for the load rating of the culvert. So I know what you're exactly talking about.
Okay.
I mean that's a negative moment issue. I mean shear will never be an issue. The concrete, the VC.
Mm-hmm.
will take the one-way shear. That's a wide element. Any slab will never have a one-way shear issue.
Yeah.
Slabs will only might have punching, which is a two-way shear issue. Slabs will never have a shear. But what you're talking about is the negative continuity and the negative reinforcement between the wall and the slab. Because the reinforcement is not coming from the wall to the slab, so you don't have negative continuity. So they are dealing with the top slab as a simply supported slab. But in reality, it's definitely not a simply supported slab. But your cracking moment capacity at the negative moment section will actually take a moment that is 40% of your mid-span positive moment.
So in the Louisiana specification, we have to rate the culvert for shear.
Yeah, any element will be definitely have to be loaded for flexion and shear, but in terms of shear strength,
yeah,
any slab element will not have a one-way shear because it's a wide element. Your VC is 2 square root F prime C BD. Your B is that wide, so you'll never have a shear problem. Unless you have a very awkward situation when you have a very high concentrated load, but I mean, the point is when you have a load on the slab, how much section width is resisting that shear load. So it's not only the area under the load. So you have to look into but in general, slab elements, they don't have a shear issue. One-way shear, to be clear.
I just want to add to your first part of the question is if you're interested in applications of FRP to culverts, Dr. Mahmoud Taha from University of New Mexico has done a lot of work in this. He's actually working on some Tran-SET / New Mexico DOT funded projects to test these in the field. So if you go on to the Tran-SET website, you'll see these documentation, and if you want his information, you can email me and I'll give you his information.
Okay, thank you.
Sure.
Can I say something? I think you're right. Shear is required to be checked for low rating. It's not for Louisiana, it's the code requirements. Every state has the same requirement. Although shear is not required to be checked for regular slab, But for box cover, the whole code was developed based on shear. I don't know why, but
Yeah.
that's what the whole thing.
Thank you, Lynn.
I don't think that's a concern though with culverts, that it's going to fail in that way. Like usually when
No.
culverts fail, it's
That's
due to
right.
strictly from deterioration
The
from the
fail-
bottom up.
Fail the load rating and the collapse, that's two different things.
Right.
So,
How we were talking
It's
about.
like what's
Right,
reality
right.
and what's right in the code.
Thanks for the presentation. I have a question about the bonding. Is the bonding an issue when you add the FRP to the concrete?
That's what we designed for. So actually, when you design the FRP, when you design your FRP, the maximum strain you can develop in the FRP is what we call the debonding strain, if it's externally bonded. So that's what you design for. That's one thing. In addition, you can enhance the bond. That's why we use a lot of the times the U-wraps. So this increases your bond capacity. The third option we use a lot of the times FRP anchors. I know they are more common for the shear application rather than the flexure application, because with the flexure, with the stresses you can develop in the FRP will get you what you want based on the debonding capacity. But yes, when you look into the design of FRP, you have mode of failure, which is the material failure, which is the rupture, or you have the debonding capacity, which is the debonding capacity that you determine based on the thickness of the FRP, the concrete strength. This is a big equation, but yes, debonding is definitely what we design for. But you can still reach for the tensile, you can rupture the material, especially if you use the anchors. And there is so many tests that have been done with so many researchers. You can rupture the FRP if it's properly anchored.
I have a question. So you said that you were using HL-3 to design for the design of the live load, right? Now you have, based on like the influence sign, do you know exactly like within the span whether you were using the tandem load or you were using the truck load?
With HL93 is actually is the 72 kip truck and the tandem. You try them both, but I'm telling you for short spans,
Right.
which is probably 30 feet or less, your tandem is the governing load. For longer spans, the truck is the governing load.
Yeah.
Because the tandem, they are 25 kip and 4 feet apart, so total 50. The truck is 72.
Yeah. So so based on that, and you in one of the slides, you were saying that y'all had trouble between the girders being too close to each other. Don't y'all have a design specification saying that the girders like having a specific distance between the girders so that they won't be able to like end up hitting one another? So y'all had to hold it up as in the jacks or something?
No, this one that when I was mentioning this about this project, this is a special bridge that the beams were just almost sitting next to each other, which is not common for a highway design bridge. This bridge is designed for much heavier loads than what we see on the highway. I think it was designed for 500.
The part of this structure.
yeah, it was not a HL93.
No, this is designed for a load that was like 10 times the truck wheel. That's a very special bridge, and this is out of nowhere and just
It's a
used for the
private
mining.
bridge, right? Like it's on private property.
Yeah. This is for
It's
owned
not
by
on
the
my-
mining company, and this was out in the coal field minings, and that's this excavator. Just the bucket. I think it's. They said what it's what. Yeah, the bucket is the size of this room. It's humongous. I mean, this is. It's something else, but I mean, in terms of spacing between girders, that's what you do, what you design for, how much spacing you need based on the size of the girder, based on the span, but that's a different issue. So I'm sorry if I was not clear about this bridge. This was a special bridge that has nothing to do with our highway bridges. I think you had
Just a question regarding the, if a bridge undergoes major rehabilitation or repair, does this mean there was a drawback in design because the designer did not maybe consider all of the environmental and loading conditions at a specific location?
I definitely can contribute to that, but I think we have also the DOT people. I mean, rehabilitation in general, let us differentiate between strengthening and a repair. So strengthening, if you are increasing the load carrying capacity of a bridge, right? Sometimes you will have a very old bridge that has been designed for a live load that's much less than what you are designing for today. That's very possible, right? So you need to increase the load carrying capacity. So that's an issue. A bridge could suffer from deterioration to so many reasons. It could be like an impact damage, that's an accident, a fire damage, which is also an accident. Sometimes it could be deterioration in terms of maintenance. There are so many reasons, but I don't think there is, I personally never seen a bridge that was under-designed. I think in general, the bridges were always designed properly according to the live loads at that time. And that's one of the things, even when we develop bridge plans, you have to put what live load you used in your design. So this will remain as part of the record of the bridge. So when we look at load rating bridges from the 30, if you look at the plan, they'll tell you this bridge was designed for this load. So I wouldn't say that it's something went wrong with the design, it's just maybe the increased load, but I'm talking also here about other structures, and we have seen this a lot in ports. Now they are trying to, because of the competition, so the main impact factor for ports is how fast they can empty the vessel. So they need larger cranes and they need larger trucks, and that's how efficient the ports will be. So they have a lot now problem that the deck was designed for a crane that's maybe like 50 ton. Now they are looking into 150 ton cranes. So they have a lot of this problem, and that's nothing wrong. This port was designed like 56 years ago. The maximum crane was 30, so they designed for 50. It never crossed their mind one day there will be a crane that's 300 ton. So sometimes those major rehabilitation, it's not because of mistake or something, it's just you need to upgrade your structure. Okay. Again, I'd like to thank you so much for your attention. I'd like to thank Dr. Hassan for inviting me and the Tran-SET for having me here today and for your attendance. Thank you so much.
Thank you so much.